Pizza seminar today, January 21st. Our speaker is Daniele Viganò. He's an ERC starting fellow at ICE and our institute, and I guess he will talk about his ERC project and something related, I guess. The quest for the exoplanetary radio emission. Daniele, go ahead.
Thank you, Luis. Yeah, indeed, I'm going to present the topic of a part of the project, the observational part of the project, which is the ongoing quest for the radio emission from exoplanets, which is something that has taken quite a lot of momentum in the last maybe 5 years or so. And there are some interesting developments. Let me first give you some brief idea of radio emission from planets for what we know before going outside the solar system. So, okay. I don't know if any of you can guess which object is this one, seen by VLA. This is in radio, some few gigahertz frequency. The size is a couple of arc-minutes. It looks like a salamander, but I don't know if anybody of you knows or wants to guess what is this. If not, I will tell you I give you a few seconds to guess if you want.
Exoplanet.
No.
Saturn.
That would be too good. No.
Saturn.
No. Sorry? Somebody else say something?
Saturn. The rings.
It's Jupiter, actually. It's Jupiter. So Jupiter is a bright radio source in the sky. This is what you can see if you go quite close to it. This is actually the emission seen by the Juno satellite. And I'm going to introduce a little bit what we know about Jupiter, just because it's the benchmark of radio emitters for planets, and that it's a little bit the main reference that we can have to think about what kind of emission we can see from extrasolar systems. So there is this kind of radio emission, that this one here that I showed you before, that has different components and somehow is related to the same belts, the radiation belts that the Earth has. So it's related to the intense magnetic field that the planet has. Intense, relatively speaking, it's more or less 10 times higher than the Earth. And so you have diffuse emission from different places above the surface of the planet. Not only in radio, but also in the UV, you have emissions which are related to the same mechanisms, and they're basically related to the presence of aurora. So these are particles, these are charged particles that are trapped and accelerated within the magnetosphere of Jupiter. And when they impact the uppermost layers of the atmosphere of the planet, they generate these UV aurora. They are pretty intense, relatively speaking. They can be seen very well. Again, these are images by Juno, by the satellite that is doing polar orbits around the planet. And the shape of the emission has some ovals which are similar to what you see on Earth. So it's a kind of cone representing the particles that impact the atmosphere. And within these ovals, you can see also the footprints of the satellites, especially Io, which is a bright spot here. And then you can see also much dimmer, Ganymede, Europa, that leaves a kind of mark on these aurora, because they represent an obstacle within the magnetosphere, and that has an impact on the acceleration of the particle. Now, the thing is that everything is, let's say, scales up with Jupiter compared to the Earth. So the electrical potential that are needed to explain this kind of emission are much stronger than the Earth, tens of times higher. We're speaking about hundreds of thousands of volts as electrical potential. And actually, you can see even, sorry for the music in the background, you can see this kind of aurora also in X-rays. So Chandra from time to time can detect this kind of aurora, which are more sporadic, and they are much more intense. They're generated by a much more intense electric field, so a potential of tens of millions of volts. And they have some peculiarities. They are different from the Earth because they are not very symmetric. The ones of the Earth, more or less, they are quite symmetric or antipodal. And they are triggered by complementary mechanism compared to the Earth. So the fast rotation of the planet, more or less 10 hours, the strong magnetic field, and the plasma injected by the volcanoes of Io helps in having this intense kind of emission across the different wavelengths. Now, going back to radio, this is what you have. This is what you can see if you look at the frequency distribution and the evolution in time. You can distinguish different components of this radio emission. All of them are quite transient, so they're represented by bursts with timescales of many different duration. They can last for hours, but they have timescales of variability that can go down to fractions of seconds. And you can distinguish different kind of wavelength. The more energetic photons come from basically the presence of IO, is the so-called IO-controlled decametric radiation. So we are speaking about frequency that reaches up to a few tenths of megahertz. And this is the only component which is visible from the ground. Because from the ground, whatever is below 8-10 megahertz is blocked by the ionosphere. So you can only see the sky above more or less 10 megahertz. So these actually are data coming from the Cassini mission. The Cassini mission and also the previous mission in the 70s, Voyager, Pioneer, could detect frequencies of the order of fraction of megahertz, and those are the kilometric radiation, and also of the order of megahertz, that is the so-called hectometric radiation. And these components are again related basically to the aurora that I showed you before. Now, the presence of IO is very important because IO, as I said before, is an intense source of plasma. So it has a lot of volcanoes, and they emit a lot of material in the magnetosphere of Jupiter. So that means that plasma is hugely available, and that creates a sort of connection. So you have a magnetic connection. You create some kind of magnetic flag tubes with associated currents flowing through it that connect the orbiting satellite to the planet. So on the planet, you can see these moving footprints represented by the presence of IO. And these electrical currents generate at some height in the magnetosphere, the radio emission. The Earth has something similar. The Earth is also a radio emitter from the space, if you look at it from outside. However, it's much, much dimmer than Jupiter, but it has some similar kilometric radiation, again, related to the aurora. Overall, this is what we can see, again, from space, basically, because except Jupiter, all the rest of the emission is below 10 megahertz, so extremely low frequency. This is what we know from the other giant planets in our solar system: Saturn, Uranus, Neptune, and also here is represented the Earth. So all of them show this kind of emission related to aurora or radio emission coming from acceleration of particles. But the only one that is pretty intense and is above the ionospheric cutoff is the one of Jupiter. And that's because of the magnetic field. The typical frequency scales with the magnetic field. So that means that you need at least a magnetic field like Jupiter to have a visible radiation from ground. Why is important the radio emission? Well, for different reasons. First, because it's a direct measurement of the typical intensity, or an order of magnitude estimation of the intensity of the magnetic field at some point in the magnetosphere. And also because if you detect the modulation, you can also have direct information about the rotation speed. So actually for Neptune, it has been used, this data from collected basically related to the radio emission from Neptune, to refine the estimate of the rotation period. Because inferring the rotation period just from the outside layers of a planet is not easy, because you have differential rotation, so it's not so trivial. Okay, the physical mechanism about this radiation. Well, you can imagine that since we are speaking about the magnetized environment, at the end, these are particles, charged particles that rotate around the magnetic field lines, and that generates some kind of synchrotron emission. However, in radio, in general, when you have a non-thermal emission and when it's coherent, like the one that we see, then you need to explain how the plasma organizes itself to give this coherent radiation. Coherent means that the particles have some kind of bulk movement, some synchronized movement, so that all of them emit at the same phase. And this is the long-standing issue of explaining the details of radio emission from many different astrophysical scenarios. For instance, in pulsars, radio emission has been known for more than 50 years. We know that at the end, these are particles that rotate, but we don't know exactly what is the plasma mechanism or the plasma instability or the plasma wave that generates this. There are many ideas, but there is no conclusive answers. And the same applies for Jupiter radiation and for planets in its extension. Now, the main candidate to explain this radiation in planets is the electrocyclotron matter instability. What you need to activate this kind of instability is a large plasma supply. And then the mechanism is the following. Imagine you have particles which are initially homogeneously spread around a magnetic field. So in principle, when they generate, they will emit, but with different phase, so that would be totally incoherent. Now, if you have an incoming electromagnetic waves that comes with the same frequency of the generation frequency, that will cause that the particles will, in one side will be accelerated, in the other side will be decelerated, and that will create a phase lag depending on the initial position of the particles. So the net effect is that all the particles will tend to bunch, in this case, around this region. If you wait for long enough, then at the end, most of them will be here, and they will move. They're not static, but they will move and they will emit at the same phase. This is why it's called maser, because it's kind of enhanced emission due to the fact that you have this synchronized movement. Other possible emission, like synchrotron incoherent or the presence of lightnings, could be there, and actually we can detect them from Jupiter at some extent, but they are very, very weak. So there is no hope to detect any of them from an extrasolar source. While this one, under proper condition, which means large plasma density and intense magnetic field, it can in principle be detected with the current and future radio facilities. And let me go to it. So what can we use to observe this kind of radiation if we want to look in some extrasolar planetary system? The king of the facilities right now is LOFAR. LOFAR is low frequency array, is composed by different stations across Europe. Most of them are in the Netherlands and in Germany. And it's composed by two kinds of antenna, the low band and the high band. Since we are most interested in as low frequency as possible, because it's what we expect to find the direct radio emission from planets is, as I said before, tens of megahertz, or if the planet is very magnetized, maybe hundreds of megahertz. So LBA, the low band antenna, is the most sensitive facility right now at this frequency, between 10 and 80 megahertz. So there are some surveys going on, and there are some upper limits, some claims that in the last part of the talk I'm going to present. Another one, which is probably not well known, is this UTR2, which is a telescope in the Ukraine. This is extremely low frequency. It's 8 to 33, so it's basically the lowest frequency among these facilities that have been used for radioplanetary searches. However, the sensitivity is not so great. It's 10 milliJASK, which is pretty high. So you don't expect really to find exoplanets or many exoplanets with this kind of flux. Then we can go a little bit higher in frequency, and then we have more facilities. This one is the upgraded giant microwave radio telescope. It's in India. Consists of about 30 parabolic telescopes, like the one that you see here in the figure. And it operates at gigahertz, but it can go down. The lowest energy channel is at about 150 megahertz, even though at that frequency, the RFI, the interference from radio frequency, become very important because the facility is located not very far away from cities. So this has been used for search for radio planets at few megahertz, and actually we are performing the analysis on some observations that we got in the last month. We had 4 observations of a given object, and my colleagues in India are taking care of that and are analyzing the data. Then there is another one which is for sure very, very well known, which is VLA, the Very Large Array in New Mexico. And that is used most of the time, I guess, in gigahertz band, but it can go down actually to 74 megahertz. So this has also been used sporadically for exoplanetary searches of radium. And then there is the Marcheson wide field array that consists of thousands of cross-dipole antennas, like this one. They look like spiders. It serves as a pathfinder for SKA, and it has between 70 and 300 megahertz, the range of frequency. And this also is a nice facility to look for radiation. Now, I've just mentioned SKA, but that will be very important when the low band, especially part of SKA, will be operative. It will consist of more than 100,000 antennas between the range of frequencies between 70 and 350 megahertz. And the sensitivity will be 10 times or even more better than LOFAR at the same frequencies. So you can reach basically a range of tens of microjansky with an integration of 1 hour. That will be in principle enough to detect the most powerful Jupiter's bursts at 10 parsec. So it becomes very interesting because potentially you really enlarge the detection horizon of exoplanets. Now, so far, what do we have? Basically upper limits on. So we have upper limits. These are campaigns that have been done, especially in the last 5 years or so. There are some which are older, but as I said before, this is gaining momentum in the last years, and it's a recent review. You can see different instruments at different frequency. You have flux density upper limits that can be in the best case of fraction of millijansky, but if you go to very low frequency, you can basically have few millijansky as an upper limit. These are targeting basically nearby hot Jupiters. Hot Jupiters are giant planets as massive as Jupiter or more that orbit very close to their host star. And for a number of reasons, they are thought to be the better candidates for radio emission, although this is kind of arguable. But they have been basically the main target for observational campaigns. And actually, this is the only, so far, claim of emission from planets. So radio emission from the planetary magnetosphere, from Tau Bootis B, which was actually the #1 candidate for this kind of emission. It has been looked many times, and with LOFAR, they reached more sensitivity that was good enough to detect this kind of signal. The signal is there now. Saying that comes from the planet or from the star is another story, and I'm going back to this in a few minutes. So there are still works going on to confirm or discard that this can actually come from the exoplanet itself. It's not clear, but it's basically the first and so far only claim for a direct emission, for emission directly coming from exoplanets. In our group, what we are trying to do, the observation I mentioned before with GMRT, the Indian telescope, we are trying to target a different kind of objects. We are targeting directly imaged planets, which in principle, they are not the best because you don't expect them maybe to be very magnetic, but this is kind of arguable. So actually there is a paper that looks among the same targets, just come out a few weeks or months ago. And so this is what we are going to look. We are going to look at nearby direct image planets as massive as possible, because in principle that will help to have a strong magnetic field. And we're going to look if we can see some radio emission. So this is the work, part of the work of our project in the next few years. Now this, I stressed many times that radio emission coming directly from the planet, because there is another related radio emission that instead has been claimed several times. That is the one possibly coming from the interaction between a star and the planet. And I start with this case, which is controversial. I mean, the detection is there, but then the interpretation is controversial. And the group of Ignacy and Manuel have worked on that as well. So this is Gliese 1151. Is a red dwarf, and red dwarfs, well, are usually a primary target for this kind, for, well, generally in exoplanetary searches. In this case, gigahertz radio emission was found, and then the question is again, does it come directly from the star, or it comes maybe from the interaction between a planet and the star in the same way that Io is triggering radio emission on Jupiter? So the way to answer that is, first of all, know if there is an exoplanet or not. So this is a system that so far has no exoplanet detected. There was a recent claim of a radial velocity detection, but it has been refuted by people in our institute, studying it with Carmenes. So it seems that the signal is really not there according to them. We can discuss it later if you want to add something. But that's not the only case so far. There is another case, which again, Gliese was involved in this paper of last year, in which they look at Proxima Centauri, that we know there is a planet discovered by Gliese and collaborators a few years ago. And they looked for some time corresponding to 1.5 orbital period of Proxima Centauri b, which is the exoplanet, the first exoplanet discovered around that star. And they find the radio emission, again at gigahertz frequency, so corresponding to magnetic field intensities of the order of kilogauss, which are proper for the star. So this is something related to the magnetic field of the star, but there is some indication that it might be induced by the presence of the planet. And a signature of that is that you can see somehow a correlation between the orbital period and the time of emission. So it seems that this emission coincides more or less with the quadrature of the planet. Though I think that, well, there will be a follow-up, I guess, because there was only 1.6 orbits covered. So maybe statistically speaking, it's not enough to say something inclusive, but it's really promising. And then very recently, there was a very interesting paper, again, basically by the same group of the first claim that I showed you before. And what they did is to use the survey by LOFAR at 144 megahertz. It's the most sensitive survey at that range so far. And at the time they analyzed the data, it was completed by 20%. So what they did was to cross-correlate the radio sources that they found with a high signal to noise, about 4 sigma, and they cross-correlated it with the Gaia catalog. What they find was the radio emission was coincident in 19 cases with the location of M dwarfs. And that 19 represent more or less 0.5% of the nearby M dwarfs in Gaia. So if you take a complete, supposedly complete sample of M dwarfs closer than 50 megaparsec between spectral cluster M1.5 and M6, that is more or less 0.5%. And among these sources, many of them are active. Some of them are inactive, magnetically speaking, so they don't show activity. And some of them, there are no data to say if they are active. The key features of this emission is that, well, the fluxes are below millijansky. The brighter temperature is very high, meaning that the radio emission is coherent for sure. And the emissions last very long, for at least a few hours. It's in all cases, it's highly circular polarized, more than 60% for most of them. And that feature is pretty different from the, let's say, the typical main sequence star radio emission that you would expect from normal plasma emission associated with activity of the star. So whenever you have a coronal mass ejection, you can also detect some radio emission associated to that. But usually that emission is either unpolarized or is polarized, but in form of short bursts, while this one is a hours-long emission. So something different has to be involved. So the point one is probably excluded. And then the other two possible mechanisms will be the electrocyclotron Meissner instability that I mentioned before, that can be triggered for two reasons. Either because they rotate very fast, and when you rotate very fast, you can accelerate particles efficiently. So you need basically that the star rotates with a period of less than 2 days, or could be triggered by the presence of a planet around the star, which is the same explanation that was given in the cases before. Now, to distinguish that, what they did is to correlate these 19 sources, the radioluminosity from these 19 sources, with the activity indicators. Activity indicators are something like H or K lines in the spectra that indicates you basically that the star is magnetically active. And also the X-ray emission is a similar indicator. What they found is that for the active stars, they do find a kind of correlation. So in those cases, actually, the radio emission could be just due to the activity. But in many cases, almost half of the sample of these 19 stars, they don't see this relation with X-ray. So they see a very low X-ray luminosity, but a high radioluminosity that departs from the phenomenological correlations that are known. And also, if they look at the period, you can see that they can detect radio emission from quite slow rotators, having tens of days or even hundreds of days. And in these cases are the most favorable to be explained by the presence of a planet around the star. Now, say that, of course, you cannot claim that there is a planet there until you detect it with another way. So a confirmation is needed by another method, for instance, radial velocity, which of course is very difficult because as in our institute, the group of Ignacy studies, when you have activity, this makes the radial velocity signal very difficult to be detected. So it has to be quite strong, otherwise you miss it. And the other thing is that you need maybe a long-term follow-up of the radio emission. So if you can see a clear modulation in the periodicity of the signal, and this periodicity is clearly different from the star's period, then this claim could be, the claim of the planetary trigger could be really more solid. And with this, I'm done. So this is what we will be working. And if you have any question, please just ask.
Okay, thank you. Thank you very much, Daniele. My camera is on. Okay. I see questions from Diego. Could you unmute yourself?
Yes, hi. Well, first of all, for those who don't know me, I am Diego. I just moved, well, yes. I'm here since July in IFAE, so next door. I'm very excited to start interacting with you guys. I know some of you already, but anyways. I have a question, maybe it's not totally related, but do you know the temperature of this, the surface temperature of these planets? Is this hot or is it cold for this radio emission to happen?
Of the planets themselves? No, because in this, well, in the cases I show you now, the last part, we don't even know if there is a planet.
Yeah, but for your estimates, if you detect one of these planets, does it need to be hot or can it be as cold as Jupiter or?
Okay, yeah, okay. Now it's an interesting question because to me it's related to the age. So I would expect that magnetism in planets, like in other objects, tends to decay with the age. So this is why we are aiming at the observation with GMRT to look at very young systems, because in that case, if the object is younger, which means also hotter, that is more likely that it will be highly magnetized and will produce radio emission. So in that sense, there is this indirect relation.
Okay. Well, the reason I ask is that well, from your talk, it came to my mind there have been some papers on using Jupiter-like planets around us to constrain dark matter heating. So the fact that if they are placed in a environment with a lot of dark matter and there is a big enough cross section, you start to heat up the planet. So, but for this, I mean, we can discuss this, but that's why I was asking this. That there is a kind of also line of research trying to use big planets which are cold somewhere to constrain how much dark matter is around. I was wondering if, because you now detect them with radio, it could be.
Well, yeah, that's actually is another part of the project that Claudia Soriano will work on, his PhD student with us. That is the cooling models for planets. There are a lot of cooling models, but there are some open questions. So probably that will enter in that line of research. Yeah,
We can discuss. Yeah.
Okay, thank you, Diego. Ignacy?
Yeah, hi. Thanks, Daniele. Very nice, very interesting. One comment and a question. The comment is that after the paper by Vedantam and the other one by Kellingham, actually, we went to the Carmenes sample and we don't see any evidence for a planet in any of those systems, actually, which doesn't mean that there's no planet there. It's just that it's below our detection limit. So there might be a chance that there's a planet at different periods or at different masses that we cannot see with Carmenes. But the planet in Gliese 1151 is really ruled out in the parameters that they gave, although it could still be like a one Earth mass planet at the, let's say, far end of the orbital distance that they're giving. So far, no planets in those samples. So unfortunately.
Okay.
And my question is, now I see that you're interested in radio emission from the directly imaged planets. So these are quite far from their star and they're young, right? So they're usually even, I would argue that they're actually really planets. In some cases, they're so massive that they might actually be formed through other mechanisms. But in any case, I don't really understand what is the source of the particles that would be causing the radio emission, because I don't expect a strong magnetized wind from those kind of stars and at that distance. So where are the particles coming from?
Yeah. No, very good question. You went to the point. Yeah. So this actually, the object that we target has a mass between 10 and 20 Jupiter masses, which means that could be a supergiant planet or could be already a brown dwarf. The limit is taken to be 13 Jupiter masses. And this is why we target that kind of masses, because we know that brown dwarfs, even when they are completely isolated, they emit very strongly in radio, very strongly, relatively speaking, but we detect that, no? So we are aiming at looking at the uppermost, well, the border between giant planets and brown dwarfs. It's not clear in that case what could be the source of plasma. One can always argue that could have some satellites, the same way of Jupiter. And if you have stronger magnetic field, everything will be amplified. It's the easy shortcut to justify the proposals, basically. No? So yeah, that's the main objection. Is the main reason why most campaigns don't look at these kind of objects. But I've seen that very recently somebody else got the same idea and they're looking exactly at the same kind of targets, even though we are using different facilities. So the portion of the sky is different. By now we are not overlapping. Yeah.
Okay, thanks.
But we should discuss about this more now that also Simran is here and we can interact more.
Indeed. Thanks again.
Okay, thank you, Ignacy. Next question is by Aldo.
Hi, Daniele. Thanks a lot. So I have a question. You mentioned just now that you looked at young objects in particular because with time the fields tend to decay, right? So in the case of stars, I see this clearly because extraction of angular momentum makes star rotate slowly, and so generation of magnetic fields becomes less efficient. But why would this be the case in giant planets, in Jupiter-like? So what would be the reason for the field to decay? Because I don't think there's so much extraction of angular momentum through a wind in this case. Huh?
Mm-hmm. Yeah, well, because in planets you have actually a trigger for the convection is the thermal gradient. Okay, so as the planet cools down, somehow the thermally driven convection can become less efficient.
So it's not rotation, but it's actually the convective velocity that would go down in this case. Probably.
Yeah, but it's not there are very few works in this direction. There are, or better say, there are very few people that work in a very nice way in this direction. One is Christiansen. There are some papers, but it's not so much studied. And these are what you are pointing out is another part of the project. So yeah.
Okay. And what would be the sweet spot in terms of generation of magnetic fields between the convective velocities and rotation velocities? So you look at Rossby numbers typically of 1 or something like this, or?
Well, Yeah, this is a good question because for these planets we don't know the rotation rate, so the spinning rate, just know the orbital one. So I'm not sure if you can say anything from a theoretical point of view. Also, I don't remember what you can say about the evolution of the Rossby number, but it's an interesting point. Yeah.
Thank you.
You have also another mechanism that is supposed to generate part of the magnetic field of the Earth. That is a chemically driven convection. It's a minor contribution, but it's there, and probably it acts mostly for the terrestrial planets. But it's basically the fact that between the inner core, which is solid in the Earth, and the outer core that is still liquid, basically some ions, some heavy ions are sinking very slowly, and some other are floating. And this kind of drifting, of chemical diffusion, can give you somehow some currents that apparently can generate some additional currents. That is.
I'm not sure if Jordi is here, but if he is, I think he will be interested in this because of a relation with generation of magnetic fields in white dwarfs, in crystallizing white dwarfs as well, which is, I think, something similar. Yeah. Okay, thanks.
Okay, thank you, Aldo. Is there any other question for Daniele? Probably Jordi, who was mentioned. Or yeah.
Sorry. Yes, effectively, it seems, but it's not clear, but that it's possible to generate a magnetic field in white dwarfs just with a similar mechanism as in the case of the Earth. You have a solid core, the star is solidified, and due to a change in the solubility between the liquid and the solid, then you have a strong convective fluid that can generate the magnetic field. The problem we have now is that we are using the approximation that they are valid for planets. It is not clear if they are valid for the stars, because the magnetic Prandtl number is completely different. And the question is if it is possible to generate a magnetic field larger than 1 megagauss. Because if it was possible to obtain high magnetic fields, we could explain the existence of these white dwarf pulsars like UR Scorpii, I think is the name. But this is an open question now.
Mm-hmm. By the way, I have on my table your paper with Kike as well of 2015. And the magnetism across different objects is very nice.
Okay, there's a new question by Fabio. Please go ahead and okay.
I was muted. Daniele, thank you for the talk. Just wanted to add a comment maybe on this last slide that you are still showing that well, tidal lock can make the rotation quite slow, but still if hot Jupiters are orbiting in like 3-4 days, it means that rotation is 3-4 days. So it's not extremely slow. So there are works showing that actually they could be in the range of a Rossby number that still allows to have an active dynamo. Still an open question. But the difference may be another. We can also talk about that. And so this kind of emission might be generated only by planets that are inside the Alfvén radius of the star. And this is quite difficult to determine actually. Even for the Sun, we know that actually the Alfvén radius was determined only recently by the Parker probe. So if they're outside, then the emission might be dominated. So the emission from the star may be actually not very easily treated. Because they are outside the Alfvén radius, and so the wind dominates the interaction between star and the planet. But we can discuss much more about that in the future.
Thank you, Fabio.
Okay, thank you, Fabio. Is there any other question? There's still time. So if you want to ask anything to Daniele, otherwise I will talk about the schedule of the pizza seminar, of future pizza seminars.
Well, I could have one more question. Then.
Go ahead, please.
Yeah, okay. So Daniele, then the spectral shape you showed in the beginning for the different planets. So the uppermost frequency would be a cutoff given by the highest magnetic field you will have. Is that this correct here? So the frequency?
Yeah.
Okay.
Yeah, basically you have a cutoff more or less of this order.
Okay. And then the intensity would then be related to the density of particles that you have producing this.
Yeah, the intensity, yeah. The intensity, this is why I mentioned that you need to have a dense environment, and this is why also Fabio was mentioning that if you are too far away, then the ECMI mechanism probably will not work. If this, I mean, assuming that the main plasma source is the stellar wind, then you need the planet to be close to the star. The shortcut to it is to say that you have something like IO that provides you locally the plasma, no? But it's of course it's speculative and it's probably not verifiable. So.
Okay. Because right, you have the problem with the moon. Because if one would not consider moons in the picture, could then this be used as a measurement of the stellar wind? In fact, I mean, eventually could not be so.
Yeah, being optimistic, yes, but
okay.
I mean, you consider also that we don't know about the beaming, so how this radiation is produced, it depends on the geometry of the system. So inferring then probably you can have some rough orders of magnitude, maybe, but still the basic mechanism is classical electrodynamic and it's okay. But then a complete model with the environment, I think, is still not very clear. Well, there are many works, but we are actually studying it now because there is a literature from the 70s going on. So,
thank you.
Okay, thank you, Aldo.